Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is section 6.4 Matrices as outside multipliers. We know that matrices represent maps um, on vector spaces, but you could also think of these maps as being kind of like an outside multiplication, even kind of making the matrices themselves as kind of like a scalar. Usually, when we do that, we make it take on a variable like x or something, and it's serving like a scalar here. So, for instance, um, right here, let's suppose that x represents like this matrix here. And so we can kind of think about how it acts on vectors in R2. All right. In fact, even like a polynomial in X. So like 2 times this matrix plus a number or something like that. How does that act on that vector? Um, okay. So what we could do is um, we could say 2x plus 3 acting on 1, 4, and this is should be an equal sign right here, acts on it because 2x acts on 1, 4, and then 3 acts on 1, 4, and you can add it, and you can see kind of what that's going to do, right? X acts on 1, 4 by its map, then that 3 acts by just multiplying to the components. You add, you can multiply 2 in, and so you actually get that this has an action. In fact, any polynomial, any like power of x, x squared, or whatever, you just multiply a to itself, a number of times, then you have a map that you can apply. It ends up being a nice outside multiplication. We're working with the ring Rx, so polynomials with coefficients in R. And we can kind of think about a vector space as being a module then, because this is not a field, the polynomials in X. However, it's a ring, and we can think of vector space like R2 as actually being a module with outside multiplication in Rx, so polynomials in X, which is kind of nice. Okay, for several reasons. Um, let's consider, okay, so let's look at notation for a minute, all right? So x times this, all right, we can think of it this way, splitting it up so 1, 4, we can split it as an addition, 1, 0, 0, 4, and x distributes the different parts. And notationally, this idea right here can actually be written this way, x x times 1, x times 4, or just x 4x. Wait a minute, x 4x itself, now this is funny. Now we have vectors that have x inside of them in places where these are actual, an x is like a whole matrix, right? But somehow it's occurring as an entry or component in the vector itself. Well, it has a meaning. And its meaning, so x 4x actually has this meaning. We have to think of it this way. So x in this component literally means x times the vector 1, 0. This one means x applied to the vector 0, 1, but then multiplying it by 4. And notice that x 4x actually as a vector, if you think about it that way, um, becomes, so x 4x right here. So using this idea right here and remembering what the matrix is, let's review what the matrix is. Matrix is right here, 1, 2, 3, 4. So A times 1, 0 is just going to be the first column, and 0, 1 is going to be the second column, 3, 2. Let's see how that comes into this computation here. So see that 1, 2, and that 3, 4. And it's 1 times that, and then just like, because it's just x times that. So it's that first column. It's the second column here, but second column because 0, 1, but then we're multiplying it by 4, of course. And then we do this addition, we get 13, 10. Interesting. So x 4x is actually equal to the vector 13, 10. So vectors that have x in them in components actually are vectors, and you can actually figure out what they are. So interesting. So if you have a vector that have x is in entries, so x is like a matrix even, it still has a meaning. and it's equal to something. Okay, so all right. Now, this is an interesting thought. If you declare that these notations, like the notation, like that what we're doing of putting x in components and multiple scalar multiplication of x are the same, uh, there's some interesting things that happen. Okay, so the outside multiplication of a matrix should be the same thing as multiplication by a scalar x. So if you multiply a vector by x, just like an outside multiplier, what does it do? It like goes component wise, right? So x times a vector just goes component, like right here, x times this vector goes component to each component, x, x. So doing that, putting x in the components like that, should be the exact same as applying the matrix. So the outside multiplier of just saying, well, okay, if I outside multiply by x minus matrix multiply, that should be like 0. Multiplying by 0 if I'm declaring they're the same. So in other words, x minus matrix should be equal to 0. Let's think about this a little bit. So what does it mean to multiply by x? That means do this, right? But this is actually represented by a matrix multiplication, this idea. What if we multiply by this matrix, xx? Notice we're going to get x4x. So outside multiplication by x is kind of like multiplying by this matrix. But wait a minute, multiplying by this matrix should be the same thing as multiplying by this matrix, which means that their difference should be the same as multiplying by 0. So we just found a 0 multiplier that has on the vector space. So this vector space, right? If we multiply anything in that vector space by this, because of the definition of what x is as a matrix, this outside multiplier should always be the 0 multiplier. This idea actually gives us a nice way of learning more about a particular matrix and map than we have before. And that's why it's in the section. Okay, so here's our matrix. Okay, if we multiply by it, that's going to be the exact same as multiplying by 0. Okay, so we're kind of merging these two multiplications, multiplying by this and multiplying by 0. Okay, so what do we have now? Now, realize something interesting. When we're thinking about vectors that have x's in the components, it's kind of like we're looking at a Cartesian product of Rx cross Rx, like looking at vectors that can take polynomials and x in both components. So we're saying, and this is like multiplication by 0 is what we're saying. All right. So doing that, so we're looking at this module here, and we say, hey, let's make this the 0 multiplier. Now, when we actually do that, something interesting happens. This guy, mod, the idea of multiplication by this is 0, actually collapses, and the quotient, or taking the chunks and whatever, collapses to just be isomorphic to R2 itself, the original vector space. Which means the original vector space can actually be thought of as a Cartesian product of Rx with itself, modded out by this guy being like 0. So it's another view of our vector space. R2 is like this guy, modded out by the idea that multiplication by this is 0. Okay, so the two ideas should be isomorphic. All right. And I guess we want to end in this little description and we actually work that idea out. Okay. So kind of what we're going to be putting our multiplication by 0 in another setting, so where it's maybe a little bit more clear. So it looks like we're going to follow an outside multiplication by 0, which is by an Rx module isomorphism. So it's like a vector space isomorphism, but it's a module isomorphism. And the way we're going to do that is row operations. Row operations, so like something that happens afterwards, an isomorphism happens afterwards. Oftentimes we can represent those with row operations before. We can do column operations, but in this case, we're going to do this when we have our scalars now, not in the field R, but in polynomial land. Okay, so we can do row operations and column operations basically in here, and then everything kind of behaves as isomorphisms now. All right. In this module sense. Okay. All right. But when we do that, so the row operation times this matrix is again going to be an outside multiplication by 0. Just keep that in mind. All right. So the result, like we do an isomorphism to 0, it's just going to be 0 again, because isomorphisms just take 0 to 0. They fix 0 there, and as they preserve the structure and their bijections. Okay, because the additive identities are sent to additive identities. Column operations, they're like pre-isomorphisms. Okay, so basically, let's see. So M, and then you do a column operation times anything is like M times something will be 0. So in our new domain, so our domain might change by doing an isomorphism before, and when we do that, then this will give a, in the new pullback domain, this actually gives a multiplication by 0. So we kind of have these ideas that we have multiplication by 0 occurring. So if we do these row operations back and forth, is just an example on this. Notice that we end up getting, we can do some to end up getting a diagonal type matrix, so zeros on the offset. So what does this mean? This means that on some pulled back domain, since we've done some column operations, that this matrix behaves like 0. It's a 0 multiplier, and it's a diagonal, which is kind of interesting, because what if we just take this this matrix, which is a 0 multiplier, and multiply it by this matrix over here? We end up getting a diagonal matrix where we have the same thing on the diagonal. Now, multiplying by a matrix with the same thing on the diagonal and 0's offset is the same thing as multiplying by a scalar itself. In other words, multiplying by this polynomial. So wait a minute. On the new pullback domain, this polynomial, multiplication by it, is like 0. Well, because of all of our row operations, column operations are isomorphisms, in an R module sense, they preserve our module structure. Multiplication by a polynomial then actually can move in and out of all the maps back and forth, which puts us into our original domain, saying that in our original domain, that's a 0 multiplier. In fact, this is what you'd call the minimal polynomial of for the matrix X that actually makes it 0. So in other words, if you actually put the matrix, this is interesting, because if you just put the matrix in right here into this polynomial, like you square the matrix, you subtract 3 times the matrix minus, and then you minus just along the diagonal. So let's write that out. When we have that, what does that mean? This is like outside multiplication by 4. Outside multiplication by 4 can be written as a matrix like this, just 4, 4. Try it, because when you multiply by a diagonal matrix like this, it has the effect of just multiplying 4 to each component, which is kind of like what an outside multiplication by 4 does. If you were to throw in our matrix X into this polynomial, you'd actually get the 0 polynomial. And that came from this Smith form type calculation. We found this. This is the minimal polynomial for X, for as a matrix, as a particular matrix. Okay. So, all right. Okay, so in other words, so this multiplies by this. So, okay, forwards and backwards. So we have our minimal polynomial, right? And okay, let's think about our desired merge. We want to take this and we want to figure out how, in doing this, performing this particular merge, how that actually makes us turn into this vector space right here of dimension 2. Okay. Um, so let's see. So we have this right here. All right. So in our pulled, okay, so this is like in our pulled back domain, I guess. So we have this, and we know this is a zero multiplier times that. All right. And we know that's going to be equal to zero. Hmm. That's interesting. Okay. So we have that. All right. So basically something in this component, it doesn't matter what is in A, that's interesting. So if we have any vector at all that looks like this, it's going to be the zero vector because it'll would have come from this multiplication. So well, A could be anything you want, but wait a minute, if A is anything you want, and then this guy right here is a multiple of our minimal polynomial, then automatically we have that we get the zero. Uh, we get the zero vector. Um, Okay, so anything, comma, any multiple of this is just 0. Okay, so AB minus, so interesting. Okay, so A, B, and CD are merged if basically they're equal to 0, kind of in this idea of how things can be 0. So A minus C can be anything you want, doesn't matter. Just if the subtraction of B and D in that component is a multiple of that, then you'd be in 0. That's kind of like um, So this is kind of like 0. Okay. So interesting. How do we know if we should merge these two guys together, right? Like, and we're thinking of A, B, C, and D as actually being polynomials right now. Those are actually polynomials. Um, how do we know we should merge them? Okay, so it looks like that really it just depends on this component. And really, we merge them like, I mean, these two guys are always, the first two guys are always basically the same merged, except that what really, as long as this guy right here, the difference is a multiple. So it kind of looks like our cosets actually come, look like this. Like we're making, like, just look at the second component. The second component looks like we're modding out by a polynomial in that component. So, and we have Rx elements in that second component, and we mod out by the polynomial. It looks like we're ignoring what's happening in the first component, and that's true. Basically, what we get is we get that when we do this mod, our Rx squared actually turns into this. Now, this polynomial factors nicely. And by the Chinese remainder theorem, since these guys don't share common factors, it actually looks like this. Now, what happens when you divide something by x minus 4 and look at the remainder? You just get a real number. In fact, all the remainders in here, every single mod actually are in here when we mod out by x minus 4 is congruent or equivalent to just r, or just a number in the real numbers. So you actually get a tuple, an ordered pair of elements right here. So we're actually getting R2, which is kind of interesting. So using this idea, we actually make our polynomial ring, or our module over the polynomial ring. So Rx2, we actually turn it into R2. So we actually turn it back into the vector space by letting X act as a matrix. And that's kind of what we did. So we're going to look at how we can use this idea. This section kind of gave us a feel for what was happening. You don't necessarily need to actually work through all those steps, at least in this book, in the exercises necessarily. There are a couple of problems that have you work through this for practice, but the main ideas that we want to glean from here, from this particular subsection, are the fact that for given a matrix, there's a minimal polynomial that makes it 0. And we can also think about vectors that have entries that look like polynomials, and they actually have a meaning. And that's because we're working in, um, that's because we are working uh, in here. Okay, this X actually means like, crossing. So looking at ordered pairs where we have polynomials and polynomials. And then when we mod out by what X does as a matrix, we actually get, this is actually going to be R2 in the mod. So R2, so what we're doing is we're actually showing that a vector space is actually a mod of of kind of like of an RX module, of a free RX module. It's a mod of it. So you mod out by something, by how we want X to be, really, and we get back to the vector space. Okay, so that concludes this little read along of the first subsection of this section. Thank you for watching.